I'm going to derive a kinetic rate expression for a Langmuir-Hinshelwood mechanism where we have two reactants, sometimes referred to as a dual site mechanism, and I'm going to do it for the case where we assume surface reaction is the rate limiting step. So adsorption, desorption, and equilibrium. So let's look at what we're talking about. The idea is that, for example, we have a surface that has various sites, all identical, where molecules can adsorb. A molecule might be here, a B molecule, maybe an A molecule, an A molecule, a B molecule. And an A and B molecule can react to form products. And we're going to look at a simplified case where these products are weakly adsorbed, so their coverage is low on the surface. Therefore, the reverse reaction is not going to be important. And we're doing this just to make it easier to understand the idea. We could certainly apply it for the case where the products also adsorb on the surface. So if we assume adsorption equilibrium, then the coverage for component A and B can be represented by a Langmuir isotherm. And in that case, coverage, so what we'll use is fractional coverage of A. So that means the fraction of the sites that are covered with A. And Langmuir isotherm, which is described in other screencasts, there's an adsorption equilibrium constant, the concentration of A in the gas phase or liquid phase, 1 plus KACA. So that's the Langmuir isotherm if we have just one component present. If we have more than one, then for B, we have KB, the concentration of B. Well, there's an analogous then expression for the coverage of B. So for the case where the surface reaction is rate limiting or rate determining, then the overall rate of reaction is the rate of the surface step, some rate constant, and it's proportional to the fractional coverages of A and B on the surface, which of course we can write in terms of the Langmuir isotherms. Now I can, and often will write this at some constant and then the same denominator, where typically the rate constant increases as we raise the temperature. So this goes up as temperature goes up. The adsorption equilibrium constant decreases as temperature goes up. So we have a lower coverage as the temperature increases. This then would be the general expression for a Langmuir-Hinshelwood mechanism with the surface reaction limiting. And so you can imagine, depending on the values of these adsorption equilibrium constants, the reaction could appear first order in A and B, or first order 1, and even negative order in the other. And so let's look at a case where if Ka times Ca is significantly less than 1, and Kb, Cb is, let's say, significantly greater than 1, then this rate expression would look like, or let's call this K double prime, Ca to the first power, and Cb to the minus power. So we can imagine the case where B is adsorbed very strongly relative to A. We can actually be negative order in B and positive order in A. This kind of thing that's seen for CO and hydrogen reacting on metal surfaces, for example, to make methane. Carbon monoxide adsorbs much more strongly than hydrogen, so the surface is mostly covered with carbon monoxide. Well, in general, let's look at what the plot would look like. So here I've plotted the rate versus the concentration of A for a fixed value of concentration of B, and I arbitrarily pick some values for the rate constant, adsorption equilibrium constants. This would be, of course, a function of temperature. You can see at low concentrations of A, it looks first order, essentially linear. At some point, it looks essentially zero order, and then at higher concentrations of A, it starts to become negative order. So as we increase the concentration of A, we're decreasing the concentration of B, essentially. We're lowering the coverage of B. We're covering the surface mostly with A, and therefore the rate's slow because we don't have much B on the surface. And there's a completely analogous plot if I did this versus the concentration of B. The exact shape depends on what's the relative values of those adsorption equilibrium constants. So this is surface reaction as the rate limiting step or the rate determining step for Langmuir-Hinshelwood mechanism on a catalytic surface.